Hello everyone, welcome to Chapter 6. This is making inferences about sample means. So with this chapter, we're going to be talking a lot about uncertainty. So when we infer a causal connection between an independent variable and a dependent variable, it's hard to know for sure whether the independent variable is causing the dependent variable. Other uncontrolled variables might be affecting the relationship too. And uncertainty will arise from the simple fact that research findings are often based on random samples. We have to use these random samples, and we rely on them because we don't have access to every member of the population. But by taking these random samples, we also introduce random sampling error. So when using a sample to draw inferences about a population, we avoid using the word certainty, and rather we talk about confidence or probability. In this chapter, you'll explore and apply inferential statistics. You're going to be learning about standard error, and you're going to be using a whole bunch of new functions. So let's begin with the local function CI95, which helps us make a 95% confidence interval. So the CI95 function uses the mean and standard error to determine the 95% confidence interval of the sample mean, the boundaries within which there's a 0.95 probability that the true population mean falls. And that's a little confusing, and it'll explain itself the further we get into this chapter. So the first thing we need to do is start this example on page 92, and we're going to be using the NES dataset, and we're going to be using the variable ftgr_gay, which is a measure of individuals' ratings of homosexuals. It is a feeling thermometer scale ranging from 0, which is cold or negative feelings, to 100, with warm or positive feelings. So we're going to be using the function wtp.t.test, and I provided the syntax in line 5. It's also on page 92 of your book. And so what this function is set up to do is to compare the mean of a variable of interest, in our case, this feeling thermometer about homosexuals, with a hypothetical mean provided by the user in the test value argument, to see if random error could account for the difference between the variable and the test value. So to reach our current objective, the mean and standard error of a solitary sample mean, we would specify a test value equal to 0, which is right here. So you want to set up your code to look just like this and run it. So as you can see from down here in the mean section of our additional output, that respondents rated gays at 51.63 on average. So our question is, how closely does this sample mean, 51.63, reflect the sentiments of the American electorate, the population from which the sample was drawn? So that answer is contained in the standard error of the mean, which is right here in our additional output, 0.377. And now that we have the standard error, we can start our CI95 function. So I put in line 9 the syntax of the function. So let's plug it in. So our function is CI95. Our mean is 51.63. And our standard error is 0.38. So this gives us, as you can see, our lower 95% boundary at 50.88 and our upper 95% boundary at 52.37. So what this means is that there's a 95% probability that the true population mean lies in the region between 50.89 and 52.37. So to be sure, there's always going to be random noise in each random sample. So on uncommon occasions, 5% of the time, we would obtain a sample mean that falls outside the boundaries, below 50.89 or above 52.37. So before we move any further, we need to talk about statistical significance. And it's pretty well illustrated on the bottom of page 93. So suppose you hypothesize that political science majors will give gays higher ratings than will the total US population. And you run the same function and you find a mean of 52 among the political science majors in your study. So it's higher than the average of 51.63, but is it statistically significant at the 0.05 level? The answer is no, it's not. And we know this because the confidence interval goes from 50.89 all the way to 52.37. So because the political science major's mean of 52 falls inside this confidence interval, we must conclude that the major's mean could have been drawn from the same population as the overall electorate. Thus, there's no significant difference. So let's apply the p-value approach on page 94, which is a more precise way to apply the 0.05 test of statistical significance. The p-value approach is where the researcher asks how often random sampling error would produce an observed difference between two means if in the population there's no true difference between them. So if it were to happen more frequently than 0.05 of the time, then we could conclude that the two means are not different. Whereas if such an event would occur less frequently than 0.05 of the time, then we could conclude that the two means are different. So on the bottom of page 94, we're going to enlist the wtp.t.test to find the relevant statistics for us. So the syntax is the same as it was up here. You can even just copy and paste it. It's great about R. And instead of 0, we're going to be using 52. So what the wtp.ttest function did was it subtracted the test value, 52, from the mean, 51.63, and reported the result, negative 0.37, in the difference section down here, as you can see. So in order for us to obtain the 95% confidence interval for the difference, we have to run CI95, typing the mean difference and the standard error. So let's take CI95 again, and we're going to be using negative 0.37 and 0.38. So the confidence boundaries encompass 0. Therefore, there is a probability of greater than 0.05 that we would obtain a difference of negative 0.37 if in fact no difference exists in the population. But how much greater than 0.05? So the answer to this is in our results right here. If our function first calculated a t statistic, or a t value down here, ours is negative 0.989. A t ratio is basically, it's equal to the mean difference divided by the standard error of the mean difference. So the function uses this calculated value, in our case it's negative 0.989, to determine a precise probability, or if you remember, p-value, right here. So our p-value is 0.322, and if in the population political science majors are really no different from anybody else, then random sampling error would give us a difference of negative 0.37 about 32% of the time. Thus, chance processes would produce the observed difference about a third of the time, which is much too frequently. You want to remember that if the p-value is less than or equal to 0.05, then you can infer that the test value is significantly different from the mean of the test variable. If the p-value is greater than 0.05, then you can infer that the test value is not significantly different from the mean of the test variable. So, in conclusion, the NES mean and the major's mean are not significantly different.